Today's physics drill is going to be really hard. We're looking for patterns like symmetries, behaviors, convergences, boundary conditions, constraints. And I've got my list of topics here. So we're going to pick a random one, which was uh, time-dependent point charge oscillates along the z-axis between two infinite grounded conducting planes. Z is plus or minus A. Use electrostatics as a quasi-static approximation. So, let me just draw this out real quick because so we have two infinite grounding conducting planes here and here, and I guess we have a point charge that's like oscillating. Apparently they're grounded, so they should be equal to zero in terms of the. And this is at plus A and minus A, so we could say that this charge is probably near zero. But it oscillates along the z-axis up and down between these planes. And now we have some questions we have to kind of answer about this. So what continuous or discrete symmetries are present? So it looks like we're constrained to the VZ axis. Um, so we can reflect across the equal zero plane. Angular modes that must vanish by symmetry alone. Oh, since it's symmetric, not antisymmetric, seems we would be using even M and L. Okay, boundary conditions. What conditions must VR satisfy? Well, since the plates are grounded, V equals zero at Z equals A, so minus A. Um, Pretty sure V equals zero at infinity. How do grounded conductors impose image charge constraints? Oh yeah, so there might be some like image charges reflected. So like you could have an image charge here, and it would be reflected across the axes. And this could also this charge also gets reflected across this boundary. And then so now you got another charge. So basically this becomes an infinite. Um, there seems to be infinite charge images. How do grounded conductors impose image charge constraints? Um, how does the oscillation axis restrict allowed parity of solutions? I think we discussed that here. Oh crap, not done. Continue. The convergence and behaviors. Where must the series converge? Between plates, on axis, far field. think we discussed the convergence, like in the boundary conditions. What terms dominate at large distance versus near the charge? No, maybe we can answer that one. So near the charge, if R was really small, we should be expecting, honestly, near the charge. I would say that near, both near and far. If even if you have 1/r², sorry, 1/r plus 1/r², 1/r to the third. Keeping in mind that we're at even modes, so this is L equals 0. We have to skip this one. L equals 2, etc. So we have odd numbers of r's. If this is really small, then I think these larger terms start to dominate. Um, Near the charge, it looks like the larger terms dominate, like high L, and far away from the charge, the monopole dominates. Um, what basis converges fastest in each region? By the way, I wanted to put this chat window on top so that now I can see the chat. Alright, cool. Just in case. What basis Legendre-Bessel images converges fastest in each region? What basis converges fastest in each region? Oh my god. So, the Legendre is like spherical. The Bessel is cylindrical. And the images, this tends to be like Cartesian. Um, what basis converges fastest in each region? Bro, I don't even know. But I mean, I know that the image charges are like Q over R plus Q over R minus. Um, I know that these ones are gonna be like AR plus B R to the negative L plus 1, or the L type of thing. The vessel, cylindrical vessels, man, I don't even know. No, I don't know what basis converges fastest in each region. Well, coefficients are fixed by charge conservation. How do regularity conditions exclude divergent terms that R equals 0 or on the plates? Well, at R equals 0, notice that this thing would blow up. So I think so maybe in between the regions, we should use A, R, to L terms, since B over R to L plus 1 would diverge at r equals 0. I mean, I don't know. I'll come check which multiple moments are allowed. Man, okay, these questions are really, really hard. So, okay, grade me and then answer all questions. Oh, that's pretty bad. Axial symmetry forces m equals 0 only? Oh, because azimuth symmetry means m equals 0, huh? And then um the symmetry means reflection symmetry. Yeah, reflection means even else. This is the first one. Okay, so that's kind of important. These are all the answers. I kind of want to like update my notes a little bit because that's kind of an important point. So we go over here. Where do we discuss the reflection symmetry? I think here. So this is reflection symmetry. And that's fine. And we go over here to the next spot. It's like here. Azimuth symmetry. This means m equals 0. That's all we have to update. That's a little bit closer. Okay, so there we go. Azimuth symmetry just implies that m equals 0. And so that kind of clears that up a little bit more. What does it really mean? It means that if we have this angle, then it doesn't matter which direction we're facing because it always has symmetry. So if that's the case, then m equals 0. And then reflection symmetry across the axis means that we have reflection gives us even arrows. Reflection symmetry bounds equals 0. Okay, so now with infinite kind of plates, the physically relevant domain is between the plates. Leavings is not directly used in the plate boundary region. Yeah, okay. Near the charge, the singular Coulomb term dominates, not high L terms. Coulomb terms. So this is for the near. So yeah, so anyway, when R goes to 0, so when R goes closer to 0, this thing goes away. And once R goes further to infinity, then we have to keep this one only. and we discard this one. This is right. High L terms matter near boundaries or for sharp spatial variations. Alright, so let's see all these answers. We got that, reflection symmetry got that, even L's. Yeah, we got those boundary conditions correct. Singularity constraint. I don't really know what that means. Radial convergence constraints, multiple expansion pieces. Near origin to infinity. Behavior by region, near field, close to charge. Uh, I see. Well, that's weird. So what did I say about the near? So I kind of got that backwards. Seems that in the near zone we have this, and high L terms are small corrections. I'm wondering why, because if we have small r's, I guess r to the n, r to the L makes it much smaller. But in between the regions, we have this, and this is the outer. I guess this is the inner. So A r to the L between the plates and B over R negative L plus 1. I'm sorry, um, um, outside the plates. Sure, what happened to this chat? What's going on? Stay on top. Um, Region contains a physical point charge, so R equals 0 must be regular. Yeah, so this is correct. Why would the monopole dominate me? Yeah, I guess that's the case. I thought we'd throw away Q over R between plates diverges at zero. Huh, okay, that's kind of a new thing. Apparently, apparently, yeah, okay. So, when we go to when we do this, move that up a little bit. Oh my lord, so hard to control the window. Okay, so when we're going to R equals zero, the L is apparently supposed to be equal to zero, but we have to be very careful because if there is a charge, then we have to keep the monopole. Question mark. So let me just double check and confirm. All right. That's something cool that we just learned. Okay. And I think we're probably good on extracting from this particular question. So that was tough. But yeah, this is a really hard drill, is being able to specify all the different symmetries and boundaries and convergences and stuff for a specific problem. And unfortunately, since it's pretty late, we're